Chapter 1, Section 4 is called Prime Factorization, and there are two key vocabulary phrases you're going to want to know before we get going too far into this. The first one is factor, and a factor is any number that goes evenly into another number. For example, if we take the number 10, we try to figure out what numbers go evenly into 10, and those would be 1, 2, 5, and 10, so we say those are the factors of 10. The next vocabulary word or phrase is factor pair, and this is two numbers that can be multiplied together to get a number. So if we stick with that example 10 that we were talking about earlier, the factor pairs would be 1 times 10 and 2 times 5. In example 1, we're going to be working on finding factor pairs, and the question says the brass section of a marching band has 30 members. The band director arranges the brass section in rows. Each row has the same number of members. How many possible arrangements are there? So we're going to do a T-chart to go ahead and try to figure out what our factor pairs could be. This is going to be how we start our T-chart, and so the factor pairs of 30 could be 1 times 30. And then we keep going down the line, 2 times 15 because 2 goes into it. Then we check to see, and 3 can also go into 30, 10 times. And we check some of our divisibility rules that we talked about in class, or we use our division skills, and we figure out 4 can't go into 30, but 5 can, and it goes in 6 times. So we have that as a factor pair. And then we notice that 6 would be the next one on the line here, but we already have it, so we don't worry about continuing that T-chart. We just go ahead and pause right there. To list out our factor pairs, we kind of take that chart and we just organize it according to those pairs. So the factor pairs of 30 are 1 and 30, 2 and 15, 3 and 10, and 5 and 6. But we do want to make sure that we go back to the actual question up here. And the question was, how many possible arrangements are there? So you could have 1 row of 30 kids, 2 rows of 15, 3 rows of 10, 5 rows of 6. But then we also want to remember that you could have 6 rows of 5, you could have 10 rows of 3, you could also have 15 rows of 2, or even 30 rows of 1. So technically, this is good enough if you were just doing your factor pair list, but to be able to answer the question, you'd actually have to put it into words and say that there are 8 possible arrangements in this case. So to finally answer the question that was asked, we would just write out this answer right here. There are 8 possible arrangements. These are the on your own problems that you have in your notebook. Here are the answers. You can check those on your own problems and see if you got them correct. Notice that in the factor pairs for the questions for 1, 2, and 3, they only list each factor pair once. They didn't double it up and then do 6 times 3 and 9 times 2 and 1 times 18. If you did that, it's okay for right now, but you only have to include it once unless it's part of answering the question. All right, and just for kicks, now you have a picture of my kitty, Pretty Princess, and she wants you to remember the difference between prime and composite numbers. So remember that a prime number is going to have only 2 factors, 1 and itself. It can only be divided evenly by 1 and itself if it's prime. But a composite number is going to have more factors, 1, itself, and then any other number that it could be divided evenly by. And if it can be divided by anything besides 1 in itself, then it's composite. And so if you at least write down the parts that are in pink and blue, that would be good enough, or you can write the whole remember box in your notes this time, but you do have to get this review into your notes, please. For example 2, we're going to be working on writing a prime factorization, and in order to be able to do that, you're going to need to know that a prime factorization is a number written as a product of its prime factors. So we're going to keep in mind that product means multiplication or answer to a multiplication problem, and we're reviewing that prime is going to mean a number that can only be divided evenly by 1 in itself. And you can use a factor tree to find the prime factorization of a number, and we're going to take a look at that in just a second. So this time we're going to write the prime factorization of 48. And one thing you're going to keep in mind is that when you do a factor tree, you can start with any two factors of the number that you want to. So I'm going to show you two options. So option one is going to be starting with the factor pairs 2 and 24. So if we start by multiplying 2 times 24, that gives us 48. And then anytime we hit a prime number, we're going to go ahead and throw a circle around that. There are different ways you can do this. Some teachers will have you keep bringing that number all the way down. I'll probably show you that on the next option so you can see the difference. And others will just have you circle it and leave it alone. We'll try that on this one just to see. And then we're just going to keep breaking these other composite numbers down. So 24, since it's composite, can still be broken down into 2 times 12. And again, 2 is prime, so I'm going to throw a circle around that. But 12 is composite, so that can be broken down a little farther. And we can do 4 times 3, or we could do 6 times 2, but I'll do 4 times 3 in this case. And 3 is prime, but, oops, sorry about that. 4 is still composite, so we're going to break that one down just a little bit farther. Let's slide this up here. And that can be broken down to 2 times 2. And so since we've got all prime numbers now, we don't have any composite numbers left at the bottom, then this is where our tree stops. For option 2, we're going to do, again, 48, just to see how the same answer can be found using two different factor trees. And this time we'll start it with 8 times 6, because that also equals 48. The book uses 3 times 16, so any factor pair will work and they should get you the same answer. And since both of these are composite, we're going to break them down as far as we can. 8 is 4 times 2, and since that's prime, I'm going to put a circle around that. And then 6 can be broken down because it's composite, so it can be considered 2 times 3. And in this case, both 2 and 3 end up being prime. So as I mentioned earlier, we can just bring those down in a second as another way to show it. It depends on what works for you. 4 is still composite, so that's 2 times 2. And now we've got all prime numbers. And so a lot of teachers will just have you keep bringing each row down until you have them all even at the bottom and they're all prime. And so that's another option. And for right now, I'll let you choose which of those makes the most sense to you. But what you'll notice here is that they both end up with all the same prime factors. So don't just count the circled ones in this case. If you drop them all down, count the end ones. Over here, if you're only looking at the prime ones, then you're going to have to just count the circled ones. But when you think about it, or when you notice here, we've got 48, and I'll just stick it in the middle because it works for both. And the prime factorization's got to be a product of all those prime factors. So over here, I have 1, 2, 3, 4 2's and a 3 being multiplied together. And over here, I have 1, 2, 3, 4 2's and a 3. So it didn't matter which way we took. We can write that out as 2 times 2 times 2 times 2 times 3. Or we can also choose to use exponents, and we can make that 2 to the 4th power times 3. And this would be the prime factorization of 48 then. Here are 2 on your own problems to try. You can practice writing the prime factorization using a factor tree for 20 and for 88. So go ahead and pause and make your factor trees for each of those. And remember to look back and remember how to write that final prime factorization. For the answers to those 2 on your own problems that I had you try, I'm going to show you again both of the possible factor trees that you could do. And you're not going to have to do 2. You can pick either one, but just while we're getting used to it, I want you to be able to see either one in case some of you did one way and others did another way. So for 20, you could have started with the factor pairs of 2 times 10, and then 2 is prime and 10 is composite, so you had to break 10 down farther into 2 times 5. Or if you chose to start your factor factor pairs with 4 times 5 over here, then 5 is already prime, and then 4 is composite, so you would have broken that down into 2 times 2. But like we're starting to see, every single time if you use correct factor pairs, you're going to end up with the same prime factorization no matter what. So either way, you should end up with 2 times 2 times 5, or you can write that as 2 to the second power times 5. For 88, again, I'm showing you 2 factor tree choices. You could start 88 as a factor pair using 8 times 11, and then you would break it down this way, and you would end up with 2 times 2 times 2 times 11, or you can start with the factor pairs of 44 times 2 and break it down this way, and you would still end up with 2 times 2 times 2 times 11. So remember again, as long as you are correctly using factor pairs and breaking everything down, then no matter which path you start with, you're always guaranteed to end up with the same prime factorization. And so we can write that as either 2 times 2 times 2 times 11 or 2 to the third power times 11. Either one is an acceptable answer.